Okay, I want to look at the next step here in our differentiation process. We looked at how to do some simple derivatives. We looked at how to do derivatives of powers. Got a couple trig functions in there, but that's about it. So we want to look now at something a little more complicated. We want to look at how we can take a derivative of a product of functions. Now, up till now, the only way we've been able to do that is if I could expand out two polynomials and then differentiate term by term. But that doesn't always work. There are some cases where I couldn't, for example, do that. What if I had something like, that would work in this case, in theory. It would work in this case if I had something like h of x equals 3x minus 2x squared times 5 plus 4x, right? We don't need anything new for that, do we? We could just expand that out and differentiate term by term. We'd be okay. But what about something like this? Won't work there, will it? That's something different. And so we need a new technique, we need new general rule to deal with something like that. So we got to develop that. And we can't. Okay, so here it is. This is what we want to do. We want to come up with a general formula for the derivative with respect to x of the product of f of x and g of x, where f of x is any function of x and g of x is any different function of x. Now let's remind ourselves real quick, because we're going to refer back to this. How do we define the derivative with respect to x of, well, let's just say h of x, using limits? Got to go back to limits. Whenever we want to develop a new standard form or you know a new trick in calculus, we got to go back to the fundamental definition of a derivative, which is the limit definition. And we can work out a trick, and then we'll just use that instead. So what is that going to be? We're used to writing this in terms of f. But we can write it in terms of h. What's our limit definition of the derivative of h of x? Limit of what? H is a bad one. I don't want to use h, do I? Because h shows up in our, how about if we call it q of x? There we go. Okay. Why not? Okay. So we get q of x plus, I think we ended up calling that an h, didn't we? X plus h minus q of x over, instead of a delta x, we just called it an h, right? To make it easier to write as h approaches 0, but either mean the same thing, right? We have to, there's our limit form, our basic general form of the derivative. We've got to apply that down here and see if we can come up with some kind of a formula. So what's that going to look like? What's the derivative with respect to x of f of x times g of x going to look like? So this is our combined, this is like q of x, right? What do you think? Ideas? What's the first part? What is, if q of x is defined as the product of f of x times g of x, what's q of x plus h? Say it again. F of x times, okay, that's q of x. You're right. What's q of x plus h then? That whole thing plus h? Not quite. Okay, good. Good. Well, we're going every place where we used to have an x, we're going to substitute an x plus h, right? So what we were previously doing to just an x, we're now going to do to the whole x plus h quantity, right? So that's going to look like, this part right here is going to look like f of x plus h times g of x plus h, right? That make sense? Okay. So there's our function our quotient, or excuse me, our product evaluated at x plus h minus plain old q of x, which is just that, right? All right. Okay, now that looks, I mean, that's really general. We don't know what function f is and what function g is. How could we possibly go anyplace with this, you might ask? Clearly this is 0 over 0. This is an odd one. This is one of the very few times in algebra where we get to add 0 instead of multiplying by 1. We always multiply by 1. It always gets all the action. But this time we get to actually add 0 in a tricky form. So let's take the same expression. This is going to be hard to fit on here, but I'll try. So there's the first term and the second term separated, but we're gonna add 0 in the middle there. I gotta change colors to do that. I'm gonna draw attention to this. Okay, here's our trick. Let's subtract and then add the same term. F of x plus h times g of x. Okay, why, you might ask, would we do that? Give me a hint. See if you can see what's going on. What if I group those two together and those two together? Can I factor, if I make these two separate groups, can I factor out something from each group? What's the common factor here? F of x plus h. Okay, so we'll take this first group. And let's go ahead and put that in brackets. So we're going to get f of x plus h times, what am I left with on top? And this is all over h. Right? What about over here? We'll take that second group. What can I factor out of that? And that's f of x times g of x. Take out g of x. Okay. Plus g of x times what's left there? F of x plus h minus f of x. Any ideas? Any ideas? Do you see anything noteworthy popping out there? You see any derivatives? Keep in mind I'm taking limits of all this stuff, right? What about this? What's that? Well, What's the limit of g of x plus h minus g of x over h? Which goes to 0. That look familiar? It's an awful lot like that, isn't it? Well, that's a cube. What is that? Another one over here. Only it involves that. What are those limits? We know those. Those are limits we've seen a lot. Isn't that a derivative? Isn't that the derivative? That limit as h goes to 0, isn't that right there the definition of the derivative g of x? Isn't that the definition of f prime of x? Okay, so we got something good going on. Let's look this thing up just a little bit more. This is going to turn out to be a nice pattern. So I've got the limit of, let's go ahead, and being as I've got, now look at this first group here, this first term. I've got this factor times this factor divided by this factor. Let's group this thing. So we've got the f of x plus h out front, and then we've got the quotient of g of x plus h minus g of x over h kind of separated out. Okay, so there's one limit. Plus, let's separate out the g of x and this limit, break it into two limits. We've got the limit of this term plus this term. We don't really need to do this, but let's separate it into two separate limits. Okay? And what happens with those? Now, if I take my limits, what is the limit of x plus h as h approaches 0? If I let h go to 0, what does that look like? F of x. Yeah. In the limit, it just approaches the function f of x. So this guy just gives us an f of x. Now, what is this whole thing right here? Did we say? The limit of g of x plus h minus g of x all over h as h goes to 0. You guys, I don't feel like that connection's being made here. Let me just pause this for just a second. You remember doing this, right, where we said the definition of the derivative, we said f prime of x equals the limit of f of x plus delta x, but we ended up calling it an h. F of x plus h minus f of x over h, right, as h approaches 0. That was our whole, remember what we did with this? It's been a little while. We've moved on to the tricks, but the reason we did this thing, we had some function f. Remember this stuff? And we said we take 2 points at x, f of x, and over here at x plus delta x or x plus h, f of x plus h. Remember this stuff? And we said we could define the slope of the secant line connecting those two by the quotient formula, right? Which is just this. Change in y, f of x plus h minus f of x over change in x, which is just called h or delta x, right? Remember this stuff? And then to make that secant line into a tangent line, we'll just move these points together so they overlap and form a single point, right? And that's how we did. You probably blocked a lot of this out because it's so laborious to do the derivatives this way. But that's how we did it, right, for a long time. We're trying to get away from that as much as we can. But that's where this stuff comes in, right? So that's nothing more than g prime of x, isn't it? Okay. Okay. Plus g of x what's that? Well, that's f prime of x, right? So look what we got. We got a formula. This derivative we were trying to figure out, the derivative of the product of f of x times g of x, look what we got. It's got two terms. It's f of x times g prime of x plus g of x times f prime of x. One of the factors times the derivative of the other plus vice versa, right? There's our formula. So let's write that. And this is what we have to work with. That's our formula. Yeah, that's all we have to do. We don't have to go through, we went through the limit thing so by way of, that's a proof. Okay, so, sorry about that. So we proved it, right? We proved it generally, and now we don't have to do that anymore. Now we've got this better form. So let's apply this to a problem like this guy that we could have done before by expanding out. We might still want to. You be the judge when we're done with this. This is an example where expanding it out might actually be easier, but this other way will work. Now, what are we calling f of x and g of x here? Yeah, okay, so we've got a product of two factors, right? And that's what this formula does. It takes the derivative of a product. So one of these we would call f of x, and one of them we would call g of x, and we'll just apply our new pattern, right? New formula. So h prime of x then would just equal, f of x. As we're going to see, it doesn't really matter which order you do these in, but we'll just be consistent. F of x times g prime of x plus g of x times f prime of x. So these are easy derivatives to calculate, right? Let's plug that stuff in. So f of x is right here. What's g prime of x? What's the derivative of that second factor? Just 4, isn't it? 0 plus 4. Plus g of x. What's f prime of x? 3. Everybody agree with that? 3 minus 4x? There's our answer. We've done the calculus. Oftentimes doing the calculus is the least of our worries. Now we have to do the algebra to simplify that down. But that's our answer. So is the algebra harder or easier here than there? I would actually argue that when you're doing problems like this, where you're just multiplying out polynomials, it's probably easier to just expand them out and do it the way we were doing it. So this is kind of a counterexample in a way. But I'm just showing you that it does work. What do we get? If I distribute the 4 down here, what do I get from that first? Minus 8. Plus, I gotta FOIL this, so what, 15 minus, what's that, minus 20x plus 12x is what? Minus 8x, and then minus 16x squared. Just add up like terms that we got, right? Okay. So in that case, it wasn't that useful. But in this case, it's absolutely essential, right? This is the only way we can do this one is by using our new trick. Now I want to show you a shortcut that I definitely prefer. Instead of writing this out, that looks a little bit cumbersome to write all those f of x's and g of x's. It's busy to look at. It's hard to interpret. It's kind of just makes you want to not look. So let's rewrite this a little differently. Let's say that we're going to define in our original problem up here. Let's define f of x as u. We do this a lot in calculus, so we're going to do this like a little variable substitution. Instead of calling it f of x, the function will now be called u. Instead of g of x, we're going to call it v. So then this becomes a lot easier to look at. It just looks like the derivative with respect to x of uv, right? U and v are understood to just be functions of x. Whatever, could be anything. Functions of x. What's our answer look like in terms of u's and v's?
U, V,
Good. It's u, v prime,
V, U.
plus v u prime. Much easier. All right, now let's apply that, our shortened version, let's apply that to this guy, one that we can only do using a product rule. So what's u going to be this time? What are we calling u? X. What's v?
Yes.
Right. All right. And what's our rule again? U v prime plus v u prime. So what's that going to equal then? We take this derivative. X, good, there's our u. What's the derivative of sine x, do you remember?
Cosine X.
Cosine x. Okay. Always do the derivatives in red. Plus v, so that's sine x, right? What's u prime? If u is x, what's the derivative of u? 1. Yeah, so we don't even really have to write it. So our answer, x cosine x plus sine x. How about that? That's amazing. Easy, right? No big deal. Okay, now you try one. Okay. Try this. Okay, try that. Now, there's a couple little things here that I'm throwing a few small curveballs at you. A few things that you got to think about just a little bit here. But give this a try and we'll see what we get. Okay, what do we get for this? Okay. Now, with this first term, Tommy had a suggestion. What do we do with that 2 maybe? Move it out front. Okay, this is a good trick. Because the 2 is a constant that's being multiplied by this product, there's no sense. Okay, you guys know where to go. By the parking lot by the gym. You know. Okay, let's finish this one up, and we'll call it a victory for the day. All right. All right. So hey, quiet. Here we go. We got to get this done. We got to jump back on track here. So this 2, we're just going to stick that out front, right? The constant we just leave out front. We're going to apply the quotient rule. I mean, the product rule. Sorry. We call that the product rule. Sorry. I meant to get the quotient rule today, but we're not going to get there. So we got the product of these 2 factors. We take that derivative. That's what's going to go in here. So what does that give us then? What is the derivative of x times cosine x?
X sine X.
Okay, good. I got x times negative sine x plus, and then plus, we did first times derivative of the second plus second times
Cosine.
times derivative of the first, which is just 1, so we don't even need it, right? So there's the first term, and then the second one is really simple. Derivative of sine x is just cosine. Okay, so that one's done. All I've got to do then is just clean things up. Distribute the 2. If I distribute the 2 all the way through, now I got that minus sign I want to pull out front, right? So I've got a minus 2x sine x plus 2 cosine x minus 2 cosine x. Right? And so here's our answer. Does that make sense?
Yeah, that's what I got.
Okay? Good. All right. Well, we got to call it our day. Victory.